Hi there, everyone. Today we are going to go over conservation of energy. But before we go over conservation of energy, I wanted to address a problem that I had gone over in our last lesson. And it was brought to my attention that there was a mistake in that question. And so I wanted to go back to it. But this is a really important lesson for everyone that we all make mistakes on these problems. And it is important for us to go back and to double check our work. And yesterday, when I was doing the problem, I noticed that there was an issue with my work, but I was doing it very quickly and I was kind of half checked in. So it's really important for us to be really focused when we're doing these problems. And I want it just to be a lesson to you guys that we all make mistakes and we can learn from our mistakes. So I do apologize that that mistake was made on your last lesson, but we're going to go over question number 5 again. Okay, so we did talk about how we have our car and our car is traveling at 18 meters per second when it applies its brakes. So it's going 18 meters per second, and all of a sudden you have a force applied on it, and that force applied is applied for 50 meters. Okay, so we end up having to figure out how fast the car is going. So we're trying to find V final. Okay, and in order to do that, we use the work energy theorem, where we know that the net work is equal to our change in kinetic energy. And so therefore we have our force applied times our distance, as long as that force applied is in parallel to the distance, is equal to 1/2 m V final squared minus V initial squared. Okay, so when I go ahead and plug that in, I get negative 2,000 newtons times 50 meters is equal to 1/2 times 1,200, being the mass of the car, times V final squared minus 18 meters per second squared. And that's where I went wrong. I forgot to include my squared there. I obviously know that that's a squared there. It just is a simple mistake. Okay. And so what I need to do is I take a look at this and I end up getting 100,000, and that's negative, is equal to 600 kilograms times V final minus 18 meters per second, and that's squared. Okay. And so when I go ahead and calculate that out, I end up getting that 157.33 is equal to my V final squared. When I take the square root of both sides there, I find that my V final of my car is 12.5 meters per second. And the reason that makes sense is because your velocity is getting slower. Your car is slowing down because the force is being applied against the car. So let's talk real quick about conservation of energy. It is very important for you to understand that the total energy for a system is conserved. And that's for any process of a closed and isolated system. So in any process for a closed and isolated system. And that's what's really important to you. Now, it is important for you to recognize that it can be transferred. It can be transferred from one system to another system, but that total energy remains the same. Okay. Our mechanical energy is equal to our potential energy plus our kinetic energy. And we did talk about that yesterday. And something that we did talk about in class today is that mechanical energy can also be written as U plus KE, because sometimes U is the symbol used for potential energy. So in an ideal situation, our change in mechanical energy is 0. So when we have an increase in kinetic energy, we have a decrease in potential energy. And so we get an equation just like this, where we have kinetic energy initial plus potential energy initial, plus then there's a new idea there, the WNC. And what that stands for is work done by non-conservative forces. So for example, like friction, heat, sound, those are all of the different things that where energy can be lost to those different types of energy, that non-conservative work. Okay. And then OE is just any other energy. Okay. So another thing that I usually write in my notes at this point is I'm usually going to write like, what can my kinetic energy be? So my kinetic energy can just be whatever my 1/2 mv squared is. But something that I can also have here, and I do want to include it here, even though we have not talked about it and it's not going to be included in this unit, but I could also have kinetic energy due to rotation. Say I had a rotating sphere, like a soccer ball rolling down a ramp or something. Some of the energy is in that rolling ball, okay? And then plus I have gravitational potential energy initial plus our spring potential energy initial, okay? And then I have plus my work of non-conservative forces. I sometimes like to do minus work of non-conservative forces. And the reason for that is because usually that's that work is in the opposite direction, like due to friction. And then that is equal to our kinetic energy final, and that's our translational kinetic energy final, plus our kinetic energy rotational final. Okay. And again, that's not going to be included in this unit, but I do want you to start thinking about that is a possibility. And then we have plus our gravitational potential energy final plus our spring potential energy final. Now, here's the deal. If you don't have kinetic energy in the beginning, go ahead and cross it out. If you don't have rotational energy in the beginning, cross it out. In these problems that we're going to be doing in this unit, I know I'm not going to have kinetic energy rotational. And so I'm going to go ahead and cross those out right away. So whatever you don't have, you can cross it out, or whatever is going to be the same on both sides, you can cross it out. Okay. So how are we going to apply this? Well, if we looked at it, we could look at it in terms of riding a roller coaster. Say we had a roller coaster cart starting from rest at the top of a 50-meter high hill. The cart has a mass of 1,000 kilograms. So you have your cart, and your cart, we're going to draw our cart here, and it's at the top of a hill, and it's going to come down, and it could even loop around into a circle. And that loop is not even going to be possible because that loop actually needs to be lower than your highest point. But something that, like, you could have a roller coaster situation like this. Okay. And so at the top of that point, you have 50 meters. Okay. And the cart has a mass of 1,000 kilograms. What is the potential energy at the top of that hill? Well, your potential energy is your gravitational potential energy, which is going to be your mass, 1,000 kilograms, times your gravity, which is 9.8 meters per second squared, times your height, which is going to be 50 meters. Okay, so we end up getting, that's going to be 5,000 times almost 10, so it's going to be close to 50,000. What is the kinetic energy at the bottom of the hill? Well, at the very bottom of the hill, all of your potential energy, your gravitational potential energy, is equal to your total energy. And at the bottom of the hill, all of your total energy has been converted into kinetic energy. So at the bottom, your gravitational potential energy initial is equal to your kinetic energy final, or your kinetic energy at the bottom there. So again, we had said that that was going to be about 500,000, not 50,000, 500,000. Okay. And what is the velocity of the cart? So let's take a look at that. If we know that the total energy, your kinetic energy, is equal to your mgh initial, and that's also equal to 1/2 mv squared. So notice here that your masses can cancel. So you end up getting that your velocity at the very bottom there is equal to the square root of 2 times g times h. Okay, so when you look at that, you get 2 times 9.8 times your height, which is 50, and take the square root of that. That's going to end up giving you 31.3 meters per second. Okay. And if you were looking at what is your actual total energy, that was going to be 1,000 kilograms times 50 times 9.8. That's going to end up giving you 490,000 joules if you are interested in that. Okay. So if you're looking at this system, okay, looking at this, how can you identify your system? So define as many systems as possible, okay? And for each system, you want to look at, does it have potential energy? Does it have kinetic energy, okay? Well, the thing that's important for you to recognize is when we're looking at just the ball alone, the ball technically only has kinetic energy. And the ball is not going to end up having potential energy if you're just looking at it as that's your only system. Because in order for you to have potential energy, you need to have an interaction between two forces because you need to have a difference in height. So technically, just looking at the system being the ball, you're looking at just kinetic energy. The ground, well, if you think about it, kinetic energy because it's moving, like the earth is moving, but really technically almost nothing because you're just looking at an atom and object that's not moving. Okay. But then if you look at your system, you define your system as the ball ground system. So the entire thing is your system. Now all of a sudden you have a gravitational potential energy up here, and then down here you're going to end up having a kinetic energy final. Okay. And something that's important for you to note from this slide is that as the ball is dropping down, you're going to, all your gravitational potential energy is going to convert to kinetic energy. So up here, you have a maximum of gravitational potential energy. Okay. And you have a minimum of kinetic energy. You have nothing. Okay. Now, when you're here at this point, half of your gravitational potential energy has been lost to kinetic energy. So you're at about the halfway point when you're at this point, kinetic energy and gravitational potential energy. And then down here, you have all kinetic energy. So all your potential energy has been converted to kinetic energy. Okay. So let's look at a pendulum system. Okay, when we're looking at our pendulum system, we want to define the whole system as the pendulum, the bob, the string, the hook, all of that. So for your system, we want to you want to look at, can it apply a force within? And the answer is no. Does the falling bob have kinetic energy? When and where does the falling bob have kinetic energy? So at this point, okay, you want to set your reference system. And your reference point, say this down here, your height equals 0. Up here, your height is your maximum. Okay. And something that's really important for you to recognize is at height max, typically, and especially, and velocity equals 0, then total energy is equal to your gravitational potential energy. Okay, or also including your spring potential energy if you're dealing with a spring. Then what ends up happening is, as you have your bob here, your massive bob here, as it goes down, it's picking up speed, so it's picking up kinetic energy and dropping potential energy until it gets to this point right here. So it's actually falling this way. Okay, once it gets to this point here, you have your kinetic energy is your maximum. Okay, so up here, you have your gravitational potential energy is your max. Down at the bottom, you have kinetic energy is your max. And then all the way back up here, you have your gravitational potential energy is your max again. And I really like the Physics Girl video where she kind of shows this demonstration where she's got a bowling ball and she holds it close to her face and lets it go, and it swings down and swings back, but it does not come back to hit her. And that's because you have conservation of energy. So let's put this idea of energy conservation to practice. Okay. We have a 3 kilogram box given a push up a frictionless incline. So we have a 3 kilogram box. It's a frictionless incline such that the initial speed is 8.6 meters per second. What is the maximum height that the box reaches? Okay. So we're looking at an incline here. And we want to figure out what is the maximum height. Okay. Well, at the very bottom of that ramp, okay, at the bottom of that ramp, you have your box, okay, and your box is given initial speed of 8.6 meters per second. Well, if I set my system up, let's look at my kinetic energy initial and my potential energy, my gravitational potential energy initial, and my spring potential and energy initial is equal to kinetic energy final plus gravitational potential energy final plus spring potential energy final. Now you might be thinking, Miss Palachek, there is no spring here. Why did you even include that? Because I want you to get used to the idea that we include it and then we can just cross it out if it doesn't exist in the system that we're dealing with. So we're not even dealing with that. Then you need to look at the very beginning. At the very beginning, you have motion. So that is definitely there. But what if we set this height equal to 0? Then guess what? We don't have potential energy, gravitational potential energy in that case, okay? We do if we looked at it in terms of a different reference frame, but we don't in terms of the reference frame we're using. Then you look at, okay, you push the box up, and as you push the box up, it's coming up this ramp, and it goes to its maximum height. At its maximum height, it stops, okay? And so therefore, we don't have our kinetic energy. So we have our kinetic energy initial is equal to our gravitational potential energy final, okay? We're being asked, what is our maximum height? So we have mgh max is equal to 1/2 mv initial squared. Okay, well, something that's really cool about this is our masses cancel. So we're looking for our height. We get v initial squared divided by 2g is equal to our maximum height. So our v initial is going to be 8.6 meters per second. We're going to square that. Don't want to make that mistake again. Divided by 2 times 9.8 meters per second squared. Okay, and when we do that, we end up getting 3.8 meters. Okay, that's going to be our maximum height. Here's the next problem. We have a ball that's dropped from a rooftop that is 12 meters above the ground. So here we have our ball that's going to be dropped. Okay, and it's going to go 12 meters. Okay, how fast is the ball moving when it reaches a point only 3 meters above the ground? So at this point, height equals 12. At this point, height equals 3 meters. Okay, so what we want to do is we want to figure out how fast the ball is moving. Now, this is going to be mind-blowing for some of you because we talked about kinematics and we looked at 1D motion. We've actually done it pretty quickly because of the way things are set up right now. But something that's crazy is you might not even use your kinematics equation sometimes. Sometimes you can just use the laws of conservation of energy because we have to look at our kinetic energy initial plus our gravitational potential energy initial. I'm not even going to include spring or rotation because it's not going to be there. And we just talked about why you would, just to make sure that you're checking your work, equals kinetic energy final plus gravitational potential energy final. Okay. Well, in the very beginning, it is dropped. And when something is dropped, that means that V initial equals 0. So we can go ahead and cancel that. So we end up getting mgh initial is equal to 1/2 mv final squared plus mgh final. And again, notice our masses cancel. Awesome. Don't always rely on the masses canceling, but in this case, they cancel. So we end up getting 9.8 times 12 meters per second squared times 12 meters minus 9.8 times 3. That was meters per second squared. This is meters, is equal to 1/2 v final squared. Okay, so then I'm going to go ahead and I am going to multiply both sides by my 2. Okay, and then I'm going to find the difference there. And actually, how I would actually plug this in is I would do 12 minus 3, which I know is 9. Okay, and then I'm going to do times 9.8 times 2 gives me my v final squared. So my v final squared in this case is going to be equal to 176.4. So I take the square root of that, and that's going to be meters squared per second squared. And so that's going to end up giving me a value of 13.3 meters per second. Okay, so it's picking up that velocity. Now you could check this work. You could check that work with your kinematics equations based on your change in y equals v initial yt plus 1/2 at squared. And you could figure that out, okay? You could figure out how much time it takes to get there, and then you could use something like v final equals v initial plus acceleration times time, okay? Or you could use v squared equals v initial squared plus 2a change in y. Now, there are all of these different things that you can use, but something that's really cool is you can also just use conservation of energy, okay? So here we have another question, and this question is involving springs, and we're looking at spring energy. A 230-gram block is attached to the end of a horizontal spring of negligible mass and spring constant of 1900 newtons per meter. Okay. So my mass is going to be equal to 0.230 kilograms. My spring constant, that's going to be my K value. How stiff is my spring? How easy or hard is it to stretch that spring? The spring is stretched back from equilibrium by a distance of 35 centimeters. So X is equal to 0.35 meters and released from rest. That's important. Released from rest. That means my V initial equals 0. What is the speed of the block when it has crossed through equilibrium and is now 10 centimeters past? So X final is 0.10. This is my X initial, and that's my X final. Okay, so now where do I go from here? Okay, so the first thing that I'm going to do is I'm going to look at what's happening here. In this case, you have a box that's attached to your horizontal spring. So we have kinetic energy initial plus gravitational potential energy initial plus spring potential energy initial is equal to kinetic energy final plus gravitational energy final plus spring potential final. Okay. Now, because we're dealing with a horizontal spring and our gravitational potential energy is not changing, we're going to set gravitational potential energy is equal to 0. Okay. Also, because my object is at rest at first, that means my kinetic energy initial equals 0. So I end up getting my initial spring potential energy is equal to my kinetic energy final plus my spring potential energy final. So when I look at that, I get 1/2 kx initial squared equals 1/2 mv final squared plus 1/2 kx final squared. Okay, so in this case, my halves can cancel, which is nice. I think it's always nice to make sure that things that can cancel, you do cancel. Okay, so I get kx initial squared minus kx final squared is equal to mv final squared. So I'm going to divide both sides by m and then take the square root of that. And now I'm just going to go ahead and plug things in. So when I go ahead and plug things in, I get that my K is 1900. So 1900 newtons per meters times X initial, which is 0.35 meters minus 0.1 meters. And I don't want to forget to square it. See, look at the lesson that I learned from our last lesson. I want to make sure that I always double check that squaring and then divide that by my mass, which is 0.230 kilograms is equal to V final squared. When I take the square root of both sides, I end up getting that my V final in this situation is going to be 30 meters per second. V final equals 30 meters per second. Okay. So one thing that I hope that you're starting to take from these problems is you always want to set up your equation. Set up your equation even if you're not going to use all of the variables, even if there's not gravitational potential energy or there's not kinetic energy in the beginning. Always make sure that you write it down because it's going to help you process and catch any mistakes that you might make. So for question number 10 says a vertically oriented spring with 2,000 newtons per meter as your spring constant is compressed to a total of 20 centimeters below its equilibrium position by a 3 kilogram block placed on top of it, and also by an additional force used to get the spring ready to launch. So when I think about this problem, I'm thinking about like an arcade game, okay? And when you have your arcade game, okay, it's like having a ball right here. Okay. And so what has happened is you have a distance of 0.20 meters. Okay. And then at that point right here, your height equals 0. We're going to set our height equal to 0. And then what happens is my box is sprung up, and this is my equilibrium point. That's my equilibrium point. And it says, if the spring is released, calculate the launch speed of the block. So I'm trying to figure out what my velocity is there. Okay. So what do? Well, I need to look at what kinds of energy I have in the beginning. So I want to look at, do I have kinetic energy in the beginning? Do I have gravitational potential energy in the beginning? And do I have spring potential energy in the beginning? Okay, I don't have friction in this case. And so then I'm just going to look at my kinetic energy final plus my gravitational energy final plus my spring potential energy final. Okay, and when I look at that, okay, I'm going to look at, in the very beginning, I don't have kinetic energy, and I set my height equal to 0, so I don't have gravitational potential energy. So I have this spring that's being released, and when that spring is being released, 1/2 kx squared, what happens is that spring potential energy is converted into velocity for the block plus gravitational potential energy for the block. So it's raising in height, but I've given it that gravitational potential energy. And then there's no spring potential in the end because we've reached our equilibrium point. Okay, so now I'm going to go ahead and plug and chug here. I'm solving for my velocity. That's what I'm trying to get on its own. So I have 1/2 mv final squared is equal to 1/2 kx squared. So k is 2,000 newtons per meter. My x is going to be 0.20, and that's going to be squared. Okay, so 1/2 kx squared minus my mass, which is going to be 3 kilogram block, times my gravity, 9.8 meters per second squared, times my height. Now, what's my height? How do I figure that out? Well, it was compressed to 0.2, and now it goes up to 0.2 meters away from what we have set for our height. Okay, and so when I go ahead and calculate all of this out, I end up getting, when I solve for, because this mass is going to be 3 kilograms. Okay, so I'm going to go ahead and bring my 2 over and my 3 over and take the square root of that. Actually, so I'm going to divide both sides by 3/2. To cancel, take the square root now, and I end up getting that my V final is equal to 4.8 meters per second. Awesome. So question number 11, we're looking at a 2-meter long pendulum. It's released from rest when the support string is at an angle of 25 degrees with the vertical. So I've got my vertical here. I have my pendulum. And what ends up happening is my pendulum ends up coming down here. Okay. So this is a 25-degree angle. Okay. Now, it says it's 2.0 meters long, released from rest when the support string is at an angle of 25 degrees with a vertical. What is the speed of the pendulum at the bottom? So this is what I need to figure out. Up here, I have only potential energy. So I have mgh initial. Down here, I have 1/2 mv final squared. And I know those two things are equal to each other. I know mgh is equal to 1/2 mv final squared. And the reason that I know that is because I don't have any other energies acting in this system. Okay, so I know that my masses are going to end up canceling, and I want to figure out what my velocity is. My velocity is the square root of 2 times g, which is 9.8 meters per second squared, times my h. Okay, but my problem is I don't know what my h is. So how do I figure that out? Well, I know that this is 2.0 meters. And I know that this is 2.0 meters. Okay, so if I can figure out what the length is of this section right here, what the length is of that section, and I'm going to call that L. If I can figure out what the length of that section is, I know that 2.0 minus h is equal to the length of that system. Okay, or length minus h, length minus h is going to end up giving me this value right here. Okay, so what I can do is I know that length right there is cosine 25. So I know cosine 25 is equal to adjacent, which is going to be 2.0 minus h divided by hypotenuse, 2.0. So I end up getting 2.0 cosine 25 equals 2.0 minus h. Okay, and so therefore I get h is equal to 2.0 minus 2.0 cosine 25. And when I go ahead and plug in those values there, I end up getting that my height is 0.187. So velocity equals the square root of 2 times 9.8 meters per second squared times 0.187 meters. Okay, and that ends up telling me that the velocity of my pendulum in that case is 1.9 meters per second. Okay, so my last problem for today is dealing with friction. In this case, I have a certain 3 kilogram object is dropped from a height of 4.2 meters. If it strikes the ground with a speed of 6.5 meters per second, how much work is done by air resistance? So what this is telling me is that I have a non-conservative force. My work of my non-conservative force is working against my energy in the system. It's almost like taking my energy away. Like if you think about it, if you're like swimming in the ocean and you're like a hardcore, you're a good swimmer, but you're swimming in the ocean, you keep getting pummeled by waves. The waves are taking energy away from you, right? So that's work done by a non-conservative force. So let's think about this. We have a 3 kilogram object, okay? And it's dropped from a height of 4.2 meters. And it's going to go all the way down. Okay. And once it hits the ground, 4.2 meters later, you have a velocity of 6.5 meters per second. So that's going to be your V final. Okay. How much work is done by air resistance? So we have our gravitational potential energy initial plus our kinetic energy initial minus the work done by air is equal to the gravitational potential energy final plus the kinetic energy final. Now you might think to yourself, why are you writing kinetic energy initial and also potential energy final? I'm just writing those so that you get used to the idea that if you write them and you process in your brain, is there kinetic energy here? Is there not? Is there potential? Is there not? Then hopefully that will help you solve the problems correctly, get the right answers. So here I end up having mgh initial minus the work done by air is equal to 1/2 mv final squared. So I'm going to rearrange this equation so that I can get the work done by air on its own. So I'm going to bring work done by air over onto the other side, work done by air, and that's equal to mgh initial minus 1/2 mv final squared. So I end up getting my 3 kilogram object at 9.8 meters per second squared times 4.2 meters minus 1/2 times 3 kilograms times the velocity squared. The velocity final squared is 6.5 meters per second, and that's all squared. And that is going to give me the work done by air resistance. So mechanical energy is not conserved if there are non-conservative forces at play. Okay, the total energy is still conserved. Your total energy is still conserved. Law of conservation of energy. Your total energy within the universe is conserved. Okay, so in this case, the work done by air is 60.1 joules equals the work done by air. Another way for you to write that is negative 60.1 because it's negative 60.1. It's work being done in the negative direction against the object. Okay, so I hope that was helpful for you today. I know, again, it's another long presentation.